what's power series? So this is a series as well, but in this case we are talking about a function, right? So this series is made up of terms like c0, c1x, c1x, c2x squared, cn x to the n, and this x can change. It's called, because of that, it's called power series. Power series about x equal to 0 means the terms are going to look like that, but a power series about x is equal to a means the terms is going to be c0 plus c1 x minus a, c2 x minus a squared plus cn x minus a to the n, etc. So that's the difference between the two. Look at that, n 0 to infinity cn x to the n. This is a power series about x equal to 0, and n 0 to infinity cn x minus a to the n. This is a power series about x is equal to a. So we have a center a here. The center here is 0, okay? And the coefficients c0, c1, cn are constant numbers. Okay. So we have this y is equal to 1 over x function here, okay? Actually, this function is looking like this, we know. But we can approximate this function by using these polynomials. Polynomials that's going to give us a power series. Look, we can take y0 as 1, y1 as 1 plus x, and y2 1 plus x squared, and then y8 1 plus x squared x cubed, blah blah blah, x to the 8. As you would see, these polynomials are getting closer and closer to this original function. This is not a coincidence, okay? We are going to see later on that this function actually can be written as an infinite sum of these things, okay? Let's look at, for example, 2 over x, and y0 is 1, y1 is 2 minus x over 2, y2 is 3 minus 3x over 2, x squared over 4. These functions that we have are going to approximate our original function 2 over x. So we are trying to use these polynomials to approximate this function. Okay, I'll tell you where we are going to get to from here. Something is missing here, I guess. And we have y is equal to ln 1 plus x, all right? Between negative 1 and 1, this y is equal to 1 plus x can be expressed in terms of this power series, x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, okay? This is not a coincidence. But outside of this negative 1 and 1, you cannot say that, look, they are just opening up, they are getting far away from our blue function, okay? Like outside of this one, they are opening up, they are staying away from it. But in this interval, they are like acting similarly. Okay, so then since we have a power series, we have to talk about the convergency at a point different from 0. If the power series converges at a point C, then it converges absolutely for all x with x less than absolute value of C, okay? Anywhere in between, it's going to be convergent absolutely. If the series diverges at D, then it diverges for all x bigger than D outside of this interval. Okay, that's the convergence and divergence of the series. That's what it means, look. So if it converges at a C, it's going to converge in between the absolute values of negative and positive of that. If it diverges at a D, so it's going to be divergent outside of this absolute value of d and on the red parts. Okay, interesting. Okay, so so it shows us that maybe there's a radius of convergence. This r actually is called the radius of convergence, right? So there's an r such that inside this negative r and r, this series is going to be convergent. Outside of this negative r and r, it's divergent. It's called the radius of convergence. Okay. Power series has a series of convergence. In this, actually, once we find the radius of convergence, then the power series is going to converge absolutely in this interval, and it's going to diverge outside of this interval. Okay, in this picture, actually, there are 6 possibilities for an interval of convergence. Here, a power series can converge in a closed and bounded interval. It can converge on a half open interval from the right. It can converge on a half open interval from the left, and it can converge on a open interval, and it can converge everywhere, or it can converge at a single point. So these are the situations that a power series can have. You can see this radius of convergence like that. So 6 possibilities for an interval of convergence for that. Corollary to the theorem 18 says if you have a power series, okay, centered at A, can be described by the following 3 cases. What are they? You can find a positive number r such that the series is going to diverge for x bigger than the interval outside of the interval, absolute value of x minus a greater than r. So this forms an interval, right, as we saw in the previous picture. But it's going to converge absolutely for x, the absolute value of x minus a less than r. The series may or may not converge at either endpoints. X is equal to a minus r and a plus r, as we said, half open from the right, half open from the left, or open interval. So that's what it's talking about here, summarizing what we had seen. And in 2, the series converges absolutely for every x. This is the situation, I think 5, E here. So in other words, radius of convergence is infinite, r is equal to infinite. And the third one, the series converges at x is equal to a, diverges elsewhere. The radius of convergence is 0, just single point. Okay, here, single point, which means just at one point it's convergent. Radius of convergence is 0. Okay. So how are we going to test a power series for convergence? We can use the ratio test or a root test to find the largest open interval where the series converges absolutely. So we can just consider an as we had, and we just use the ratio test for that. Okay. And if R is finite, which means radius of convergence is finite, test for convergence or divergence at each endpoint. We have to test it at each endpoint. Okay, we have to do it separately. We can use a comparison test, we can use integral test, alternating test to do that. If R is finite, if R is finite, the series diverges outside of this interval. Okay. Okay. And here there's a note that it doesn't even converge conditionally. Okay, this happens because the term doesn't approach 0 for those values of x. This is just a small detail here. Okay, let's say I have 2 series and I want to and let's say they are converging absolutely with the same radius of convergence. Okay, with the center 0, and I want to multiply them out. I can multiply them out and form a new series, and when I do that, Cn is going to be looking like this. This is the new coefficient of the product, okay, like this. And I form a new power series here, and this new power series is going to be converging absolutely to the product of the two, ax bx, in the same radius of convergence r. That's very nice. So I have this series, I have this series, I multiply them out, and the new power series that I get is going to converge in the same radius of convergence. That's very good. And also it's going to converge to ax times bx. Very nice. Okay, so this is as you would know, if you have a series that's converging absolutely in the radius of convergence r, and if you have a function f, if we compose f with x, then the new series that we get is going to be converging absolutely, and it's going to converge for all x where the absolute value of f is less than r. So let's say we start, this theorem 21 is important, is useful. Let's say we start with a power series with center A, and the radius of convergence r, that's positive. And let's say it defines a function f of x. This is the function it defines on the interval. This is the radius of convergence interval. And this function has derivatives of all orders inside that interval. So you are allowed to take the derivatives of each, and when you take the derivative, you can take the derivative of the term by term. If you take the derivative of this, you get n times Cn times decrease the power by 1. And you take the derivative twice, you get that. But we observe that it started from 0, and then n equals to 1 and n equals to 2. You are losing the first term, which you're losing one term, which is actually a constant term. If you take the derivative, it becomes 0. Okay, very nice. And then can we do the integration, term by term integration? In the previous one, we were able to do term by term differentiation. In here, can we do the term by term integration? Yes, we can. Again, we have the power series and we have the radius of convergence here. Then we just integrate. And what if you integrate this inside term, you increase the power by 1, divide by it, you get this expression, and it's going to be still convergent in the same radius of convergence. Okay, and don't forget to add a c, because this is an indefinite integral. That's all good.